Swayam Prabha. Digital India. Educated India.
Let us look at more specifics on analytical expressions of things. Analytical expression, just like we did it for exponential growth, let us take a quick look at what we have here. The underlying equation is ds by dt is s star minus s divided by the adjustment time. This is what we already have. Let us follow the same scheme that we did. ds by s star minus s is equal to dt by at, integrating both sides 0 to t ds by s star minus s 0 to t dt by at is a single variable, which is minus logarithm of s star minus s of let us just make it tau 0 to t is equal to what is it, t by at. So here I have logarithm of s star minus s of time 0 divided by s star, t s star minus s of time 0 minus t by at, which will be equivalent to s star minus s of time t divided by s star minus s of time 0 e power minus t by at, which means my s at time t is equal to s star plus s naught minus s star e power minus t by at. Again, these are linear systems. There is no non-linearity, hence we can nicely solve it like this. Stock at time t is desired goal of this system, s star plus initial stock minus the goal d power minus t by at. So, e power minus x should be the expression, because you can look at the curve that is happening. So, it is e power minus x, so e power minus t by at. So, given the goal as well as the initial stock, we can compute what happens at time t for whatever values. We need to know at, we need to know s star, and we need to know s naught. So, s star is the goal, s naught is the initial value, at is your adjustment time, of course t is the total time limit, right. So, one of the thing we saw was when adjustment time 80 units passes, then what happens? When time of 80 passes, what do you get? S at t equal to 80 ds star plus s naught minus s star e power minus 80 by 80, which is e power minus 1, which gives s star plus s naught minus s star into 0.3678 e power minus 1. So, s at time t equal to at will be s naught plus 0.632 times your S star minus S naught. As time unit of AT passes, we adjust 63% of the discrepancy. Using a simulation, since time step was 1, the resolution was not great. So, we took it about 60 to 65%, but if you reduce the time step, you can see that the 63% of discrepancy is about 63% of discrepancy is adjusted for every time period 80. So, 60% discrepancy adjusted for every time period 80, right. So, what we mean is, if you have the graph like this is your stock, this is your time. So, if we call it 80, 280, 380, and you get it like that. Stock is changing from across time 0, 80, 280, 380 times, etc. So, up to this will be 63% of S star. Here initial value of stock is 0, right. So, wherever it is reaching, that is your S star. It is reaching at infinite time. So, that initial value is 0. So, 60% discrepancy is fulfilled when 80 time period passes. So, at this point, at time 280, 63% of S star minus S at time 80 is satisfied. So, every time unit 63% of the remaining discrepancy gets satisfied, increment, and so on until at 380 again it is 60, again some discrepancy gets satisfied, etc., and reaches your goal asymptotically. Yeah, sorry, the graph didn't come out very well, but it serves the purpose. The idea is 60% discrepancy adjusted for every time period 80, so the remaining discrepancy. Now, in last class we saw an rate level plot. We had the level on the x axis and rate on the y axis, and we saw that it has any positive slope g, then you will have exponential growth. So, this is a goal seeking system. So, you have a negative slope, right. So, when as we any negative slope system, as example that shows here the equilibrium point is at 100, because 100 was the goal of the system. The goal defines the equilibrium point. So, any push on either direction will bring the system back to that same equilibrium point. That is how system is going to go, and any again depends on the slope, it will affect the time at which it takes to reach the equilibrium, and that is f nothing but 1 over 80. Yeah, time constant adjustment time is 1 over f, time required to reduce 63% of discrepancy, smaller 80 corrects discrepancy faster, larger f corrects discrepancy faster. We will stop here, and next class we will look at system compensation. When there is other, how do you control when there is uncontrolled variables in the system also.